This is Cosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen, viewers and listeners, trolls and lurkers. This is the Cosmographia podcast. We are here once again with Bradley. How you doing, Brad?
Amongst it all, I'm quite good. But, you know, I shut down the TV months ago, and I'm in a small town, and I work out of my loft. So not too much different for me, but, you know, I feel good. But it's a weird place we're in.
What's the image you got behind you today for this show?
Well, this is when we started getting into multiple disintegration of Comet Schwarzmann-Wachmann.
Mike, sir.
Howdy.
How are you doing? Everything going okay?
Things are good here. Thank you. Everybody's fine. No problems here so far.
All right. And Randall, sir.
Here I am.
What's the image you got today behind you?
Well, this is one I found, and I believe right there is Comet Atlas.
Ah, yes.
I'd like to attribute this image to whoever took it, so I'll try to find out before we're done. But it's a beautiful image of Atlas right there.
It's nice emerald green. Yeah, it's beautiful.
Yeah.
I think Kyle was going to tell us a little bit about Comet Atlas.
Russ knows everything about Comet Atlas.
People are screaming that it's 4 times bigger than Jupiter, and why are we not talking about it? So maybe we ought to say a word or 12.
Well, that's why I was going to defer to Kyle. But before we start that, I just want to make an announcement that I'm really, really excited about. There is right now, as we speak, in creation, taking shape, as we speak, a Normal Guy t-shirt.
That's right.
I haven't seen it yet.
I'm both really flattered and afraid.
I'm really looking forward. My heart is palpitating a bit at the thought of it. Okay, so I just wanted to get that out there.
May or may not involve a crystal spaceship, I believe.
Right. It's possible that there may be a crystal spaceship.
And it's possible that the crystal spaceship may have a pilot.
That's right. Wow. It may be being piloted by a normal guy. Also, of course, the silent mic, which we showed on the correspondence episode, that's going to be made into a t-shirt as well. There's a whole bunch of stuff like that we're working on. So it's going to be very exciting.
Okay, what you got for us, Kyle?
Well, I have an article from space.com.
Good source.
Yeah.
Space's website.
Bright Comet Atlas visibly appears in April. And I guess right now it's visible with high power binoculars, obviously telescope. But it's interesting. I guess the computer models show that its trajectory is the same as the Great Comet of 1844, which you know about. I've not looked into that one.
Yeah, it's one of the great comets of recent centuries. I think, if memory serves me correctly, it was mostly visible, though, from the southern hemisphere, New Zealand, Australia, places like that. But I don't recall.
Well, if that behind you is a picture of current Comet Atlas, that's got to be the southern hemisphere because I see a galaxy down there. That's got to be right. So that must be.
Yeah, although comets usually are going to be visible from the whole planet.
Yeah,
but it just depends on where they are relative to the plane of the ecliptic when they make their perigee, which is their closest passage to Earth. Are they going to be in the northern hemisphere or the southern hemisphere? Because usually, comet orbits are going to be tilted to the plane of the ecliptic, right? So typically what will happen is they're coming in, they might be north of the plane of the ecliptic, celestial north, then they cross the plane of the ecliptic, they're now in the south. And of course, it's doing that. Where's the Earth in there? So obviously a comet's going to be the brightest at perigee. Perigee is, of course, the closest passage to Earth. So I remember when.
So then,
yeah, go ahead.
And then the difference between perigee and perihelion. That's closest to the sun, correct?
Closest to the sun, correct.
There we go. Yeah, just to differentiate that for people, perigee and perihelion.
Yeah, perigee. There's G where you get geology, geography.
Geo, yeah.
Geo, right.
And so check again. We've learned that I may not be perfectly right on my numbers here, but it was going to be 72 million miles away from Earth, so it's not going to be very close to the Earth.
No.
But we still possibly that we're going to be able to see it with naked eye, depending on if it makes it around the sun.
Mm-hmm.
Yeah. Well, I got this. This is a pretty interesting excerpt from this article. If you want me to read it.
Yeah, please do.
Sure.
Okay, so this is about halfway through the article. They're saying the best way to determine if a comet is going to put on a good show is to pin down whether it is a new comet moving in a parabolic orbit, that is, one that originated from the Oort cloud. Comets that have been around the sun before will appear to be traveling around our star in the shape of a stretched ellipse because gravitational interactions during their journeys through the solar system have reshaped their orbits. New comets, on the other hand, travel in parabolic orbits because they literally fall from the depths of space towards the sun in a straight line, swing around the sun, and then are flung back out into space. Such first-timers have never interacted with the sun before and are covered with very volatile materials such as frozen nitrogen, carbon monoxide, and carbon dioxide. These ices vaporize far from the sun, giving a distant comet a rapid surge in brightness that can raise unrealistic expectations. But once those ices are gone, the comet's rapid brightening dramatically slows. But Comet Atlas doesn't appear to be a newcomer. We already noted that its orbit closely matches that of the Great Comet of 1844. Both appear to be following trajectories which swing out far beyond the outer reaches of the solar system and taking around 6,000 years to make one complete orbital circuit. In essence, both comets have circled the sun at least once, if not more than a few times.
Mm-hmm.
So a well-known comet expert, John Bortle, I'm not sure how to pronounce his last name.
Spell it for us.
Bortle.
Okay.
Bortle
it is.
Bortle, yeah.
John Bortle believes that Atlas is basically a significant chunk broken off of Comet 1844, probably during the sunward-bound leg of that comet's journey some centuries ago. He says, what is approaching the sun now is a modest-sized piece of cometary ice and dust with a large, freshly exposed portion of surface, one that's never seen the sun, such that it reacts to sunlight similar in the manner of an Oort cloud comet, like Comet Kohoutek.
Yeah, Kohoutek, which was 1973.
Yeah, back in 73. Intrinsically, it is probably several magnitudes fainter than we currently assume it to be, and may or may not be large enough to survive perihelion passage.
Mm-hmm. And if it does not survive perihelion passage, it'll undoubtedly end up being sucked into the sun.
Yeah.
And which case, and we're going to do a future program on this, the discovery of sun-grazing comets and the potential effect that infalls of sun-grazing comets have on the stability of the chromosphere and photosphere of the sun, and the possible connection between the infall of cometary nuclei and coronal mass ejections and solar storms and so on. Which I think could be a potential link between two very, at this point, still disparate phenomena, solar phenomena and cometary phenomena. And it may be a way to actually reconcile some of the potential effects of both of those kinds of phenomena on the Earth. Go ahead. Sorry.
Well, the last thing was about viewing it, so I'll just read this. From now through April 10, those who try searching out for the comet are going to be handicapped by the presence of the moon, which will turn full on April 7th. The moon's dazzling light is going to make a sighting of this dim, wispy object all that more difficult. On a positive note, its path through the constellations will continue to be very favorable for northern hemisphere observers, as it will remain circumpolar, always remaining above the horizon.
Okay.
As darkness falls, it will be positioned more than halfway up in the northwest sky. The comet currently resides within the boundaries of Camelopardalis, the giraffe, a rather dim, shapeless star pattern. There it will stay right on through April.
So it'll be in the undying stars. Is that what they're saying? Is that what they're talking about?
What are the undying?
They won't. Well, maybe never mind. But yeah, so Randall, that image behind you was taken from New Mexico.
Okay.
On March 18th.
Do you have who took it so we can give him a shout out?
Let's see. Rolando Ligustri, the Kara project.
Okay.
And it was the galaxy there to your right is the M81 and the M82. There's two of them there, M81 and M82 galaxies.
Yeah, below your left shoulder.
Yeah. Below your left shoulder. On the right where I'm looking. Yeah, so I thought that might be Andromeda, which was why I was thinking Southern Hemisphere, but no, it's M81 and M82.
Okay.
So what it made me think of right away Randall, just for a comparison, it made me think of Comet Holmes, which came around in 2007. People were exclaiming that it was, almost as big as the sun. It's multiple times bigger than Jupiter, but that's not the nucleus itself.
Right.
Comet Holmes in 2007, it's on a 7-year cycle. It came around in 2014 and is due again next April, actually. So about a year from now, or February maybe. Its coma with the outgassing was larger than the sun, but the nucleus itself was 2 miles.
Right.
2 miles. Yeah. So, it's got some gas in there, and like that article said, it might be its first exposure to the sun. So it's really gonna, let that stuff go, release its captured gases, and may be quite spectacular. But then it may fizzle really suddenly. But we don't know. You can't really predict. You don't know how many gases are in there.
Let me mention that it made references to the geometry of cometary orbits in the article you read, referring to the Oort cloud comets having parabolic orbits, and we'll call them the Jovian comets having elliptical orbits. And I mean, of course, an ellipse is one of the conic sections, and it's closed. See, a parabola is open, and I have a little graphic here. I can show you real quick. So you can kind of see
graphics.
I do. We like graphics. We do. Let's see here. Share screen. Okay.
Yeah, we see it.
Here we go. So you'll notice here that this is why they're called the conic sections. And what we have here is a cutting plane perpendicular to the axis of the cone, and that gives you a circle. But when you start tilting the cutting plane to the axis of the cone, you see what happens is you start introducing this eccentricity into the circle. And so what happens is, rather than a single center and a circumference, you now have a circumference and two foci, or two focal points that begin to spread apart along what's called the major axis of the ellipse, which is the long axis. And the further apart those two foci go, the flatter the ellipse becomes. And then if you continue to tilt the cutting plane, you see over number 1 here is that the cutting plane is parallel to the slant of the cone. And at that point, what's going to happen is the ellipse opens up, becomes open-ended, see? So when you look at a comet and you see it traversing in its orbit, once you plot enough points, an astronomer is going to be able to determine, okay, these points define an ellipse, which means it's a closed orbit, which means it's going to have some periodicity to it. It's going to go out presumably somewhere in the vicinity of Jupiter, and then it's going to turn around and it's going to come back in. If it shows up to be a parabola, you see, this parabola is now open. Now, it could be that the parabola really is a hugely massive ellipse, but our section of it is not enough to determine because once you get that cutting plane close to the slant of the cone, at that point there's a very, very subtle difference between an ellipse and a parabola. But specifically, a parabola is going to be open-ended. So what that means is, rather than being periodic, the comet is coming in from deep space, it's captured into the solar gravitational field. It comes in and it loops around and then it heads back out. And presumably, if it's on a parabolic orbit, it ain't coming back. Or it's coming back so far into the future that we can't determine its periodicity.
Like that object Oumuamua that did that. It was the long cigar-shaped asteroid body that came in from deep space around the sun and went back out, and
it was parabolic, wasn't it?
Right, it was parabolic. It was a one-time deal.
And then, of course, once you get the cutting plane parallel to the axis of the cone, now you get the hyperbola. So these are the properties of conic sections are, to me, just incredibly fascinating. But yeah, this is the mathematics that describes orbits. So maybe at some point we can have a lesson on the geometry of the conic sections and
also the Carolina Bays.
Yeah, absolutely.
Right.
Anything that's elliptical or well, for example, there's one of the properties of the conic sections is with parabolas. You know that you look at the lens of a flashlight or a radar dish, they're going to be parabolic in profile. And the reason for that is because a parabola has a focal point, just like an ellipse. An ellipse has two focal points. You know, in the old days, architects knew about this property, of ellipses where, and at some point I can have another program where I can show all of these graphics and things. But what happens is vibratory phenomena, wave phenomena that's going outward from like a point source. If you've got, let's say you've got an ellipse and you've got a source of sound waves and it's on the focus, one of the two foci of the ellipse. You project a sound outward and that sound is going to move outwards and it's going to bounce off of the sides, the walls, if you will, of the ellipse. And where it converges is to the opposite foci, you see? So architects knew that they would create these whispering galleries where you have these big rooms, and if a person was standing on one focus and another person on another focus, the very smallest sound would get amplified and sent back to the other focus. In parabolas, the phenomena comes in, and it can be light waves or it can be sound waves coming in, will hit the parabola and then be reflected from the parabola right to the focus. See? Or likewise, in a flashlight, you've got the point source of light. The light waves come out, hit the parabolic shaped reflector, and are then sent out in parallel lines. So they got very interesting properties. And I don't know, I forgot really where I was going with as far as how that was connected to cometary orbits, but typically if you have a Jovian comet, you might have, and it's an elliptical orbit, Sun at one focus and Jupiter at the other focus.
Okay.
Mm-hmm. Whereas a long period comet, an Oort cloud comet, has just got the one focus, which is the sun. The sun is going to be the point, you see.
Like you said, you could get into a whole detailed explanation of that. We could spend a whole episode on getting into the conic sections and the parabolas and the
that would be fun,
and all those possible orbits of objects coming in and out of the solar system. Heck yeah.
I get really high on the conic sections.
I know you do. We can go there. High is good.
So, yeah. So you guys had a conversation with Chandra Wickramasinghe, and one of the things that I have been really fascinated about is exobiology. the idea of organic material being delivered to Earth from space. I've done a bit of research, but it's very, very fascinating, and love to jump into it more. Back in, oh gosh, when was this? I think this was in 2014. I wrote an article about some of the ideas of exobiology. And okay, 2014. So this would have been 6 years ago. And I just a little extract from this article. And I said, in the late 1970s, there emerged a compelling hypothesis regarding the emergence and evolution of life on Earth. Formulated by Fred Hoyle and Chandra Wickramasinghe, it proposed that life did not first begin on Earth, but originated in the astronomical realm and was delivered to Earth via celestial objects, primarily comets. This idea necessarily supposed the origin and existence of life, or at least the biochemical precursors to life, to be somewhere else in the universe. The term now used to designate study of this scenario in all its ramifications is exobiology. To be sure, others had proposed theories promoting the extraterrestrial origins of life. In the 19th century, Kyle, I'm sure you will recall that Flammarion, Lord Kelvin, and Hermann von Helmholtz all suggested that terrestrial life was not a homegrown phenomenon, but originated outside the planet, elsewhere in the universe. At a meeting...
Yes, Lord Kelvin, of course.
Yes, you remember Hermann von Helmholtz?
Yes.
Of course you remember Hermann. And that's different than Hermann Munster.
Is he the guy who invented the Helmholtz resonator? That might be getting off topic.
That would sound logical.
Is Lord Kelvin the guy who came up with the Kelvin scale
yes.
temperature? Okay.
Yes.
Okay, I bet it is.
Same
the
guy.
Helmholtz
Same
resonator.
Guy.
Yeah.
Yeah. Okay.
Very interesting for pyramid theories.
Yeah.
So. Right.
Same. Christopher Dunn.
At a meeting of the British Society for the Advancement of Science in 1871, Lord Kelvin speculated on the possibility that meteorites had brought life to Earth. In 1908, same year, of course, as Tunguska, the Swedish scientist Arrhenius wrote on the feasibility of life migrating through space. Arrhenius coined the term panspermia, which basically means seeds everywhere, to describe this process, and is now considered the founding father of the field of exobiology. However, science at that stage of development was not capable of providing actual evidence that could confirm or refute the notion of a cosmic origin to life. So for most of the 20th century, nearly all scientists viewed the Earth as a closed system, until the aforementioned revival by Hoyle and Wickramasinghe. Since they first published, our understanding of cosmic processes has evolved. We now know that prebiotic material is exceedingly robust, making it more likely that it could survive an interplanetary or even interstellar journey. In 1986, a flyby of Halley's Comet detected the presence of organic materials. In 2004, a close flyby of Comet P/Wild registered the spectral signature of organic material present in the dust being ejected from the cometary nucleus. Cosmic dust has been collected directly from the atmosphere, by airplanes and balloons. Samples captured at an altitude of about 25 miles showed the presence of biologically active materials of an indeterminate nature. An extremely important advance in evolving models of exobiological processes came with the fall to Earth and swift recovery of the Murchison meteorite in 1968. An analysis of meteoritic material revealed the presence of 74 amino acids, of which 55 had no known counterpart on Earth. This find confirms conclusively that prebiotic chemistry has an extraterrestrial existence, and there exists a mechanism for the delivery of this material to Earth. So now, from there, let's talk about Wickramasinghe and your interview with him and his possible connection between deliver of microbial material to Earth and what's going on right now.
Yeah, well, we talked to Dr. C, as George Howard calls him. Okay. We talked to him. Yeah, we talked to him for more than 2 hours, and it was amazing. But there were things that stood out to me. He gave us he gave us a rundown of the timeline of the things that he's been working on. The first thing that I really found fascinating was the discovery of the absorption spectra in infrared light of interstellar dust, and that it's organic, like not ice crystals and other simple silicates or whatever that long had been thought, but that it actually is complex organic materials. Not necessarily organisms, but that the absorption spectra shows complex, what he called complex organic particles. So that was really interesting. And I mean, that to me, so that means like these enormous interstellar dust clouds that are out there are made of complicated organic chemistry at the very least. So like what you were saying, like prebiotic material. So that was really interesting. And he talked about the various studies they did with balloons. First, there was a mountaintop study and how much biological material was hitting these mountains. Was it the Sierra Nevadas?
Yeah, I can't remember. I think it was.
And so that those mountain peaks are a certain amount high. And then he said that they were like 41 kilometers up with balloons, and they got. I can't remember, what was it, 1 million. What was the numbers?
Well, the amount of virus based on the study on the mountaintops, they had these basically collector plates.
Yeah.
And they figured the amount of viruses that fall on every square meter is 1 billion.
Basically 1 billion viral particles per day on every square meter.
Every square meter of the planet.
That settles it. I'm not going outside anymore.
Right.
Yeah, it was outrageously large. I remember that.
Yeah.
And outrageously unexpectedly large.
He was saying 3 tons of biological material, or the equivalent of, almost 1 billion viral particles per square meter per 24 hours.
Yeah. Wait a minute. It said 3 tons on every square meter.
No.
Every 24 hours.
I think the idea was 3 tons total.
Yeah.
Per day.
Oh yeah. Okay. Over the whole planet.
Yeah. Something like that.
Yeah. That sounds reasonable.
Yeah. Right.
Because I was saying if it's the latter, then that would explain why I've been feeling kind of sluggish when I've been.
Yeah.
Right.
Another way to say it.
3 tons of bacterial weight on my shoulders.
Right. Yeah. Another way he put it was that they found that in every drop of ocean water, there's 1 million viruses.
And most of which are not categorized.
Mm-hmm. Yeah. And so, and the fact is that the sun is constantly destroying these things.
Mm-hmm.
And so they've got to be being regenerated or replenished. How are they being replenished? How is every drop of ocean water contain 1 million viruses if the sun's destroying them all the time?
What does Chandra say?
He thinks they're infalling.
They're falling.
Okay. Yeah. Okay. Well, yeah. Then right.
Yeah.
Right.
And so I asked him about, I was like, well, okay, if the sun destroys them in our atmosphere, and that we know that there's hard radiation out in space, you got alpha particle radiation plus gamma rays and stuff. How do they survive out there? And he said, well, they can be preserved in these little tiny dust specks, and they're inside the dust specks. They're basically completely protected. But once they get down here, the dust or whatever, it dissolves in the water or falls apart in the atmosphere, and then the viruses, all the materials released into the atmosphere openly, and then then they start infecting things or they get destroyed. So,
mention about his 79 or 77 book, which like I said, I read way back then. Loaned my copy to somebody, which was a big mistake. I don't loan books anymore. But
Disease from Space.
I don't recall a lot of detail about it. So he must have spoke about the idea of diseases from space and the current pandemic. Did he? Was that when did you guys have this conversation?
It was last Saturday. I guess.
Oh, okay. So that we
not this. Yeah, a week ago.
Yeah, but we were still close enough that we were into all of this at that point.
Sure.
Right. Yeah. And we did talk about we went through some of the evidence that he put in the book about there's unexplained spread of plagues in history, how it would appear in various places, like the one he talked about, a lot was the Spanish influenza that showed up. It appeared on the same day in Bombay, in India, and in Boston in the United States.
Yeah, how the hell do you explain that?
Right. And then from Boston, it took 3 weeks to get to New York. So how did it show up in Bombay and in India, and in Boston on the same day?
Exactly.
Well,
right.
I have a question here. Why then, if given this idea that all this stuff is filtrating down from space, why do these things seem to vector back to Asia?
Well, we did talk some about that, and he talked about how it's atmospheric stuff, and he showed how there's a latitude band that you can often see, so it comes in, and then there'll be pockets where it is able to come down to the surface. But most of the time, he said, once they get into the atmosphere, they may stay there for years before they get down close enough to the surface where they start affecting things. And that's that has been shown by the balloon studies where they're looking at stuff that's way up there. And it takes a long time for that stuff to percolate down to the lower levels of the atmosphere. But some places there are just holes where it can, the equivalent of a hole where it can fall to the surface. And then once it gets there, if it's infective on some life there, then it will spread through regular, medical vectors, basically.
And it could be that, susceptibility to infection by the viruses may have a cultural component.
Yeah.
Yes,
that's true.
Mm-hmm.
And
that was sorry, Russ. That was episode 141 for you guys, Brothers of the Serpent podcast, and it was excellent. And I learned so much, and I feel like I didn't even get half of it, and I need to go listen again.
Oh well,
so,
thank you.
Yeah. Everybody should go listen to the Brothers of the Serpent podcast number 141 with
141.
Dr. Chandra Ramasinghe.
Yeah.
Is that how
he blew our minds?
The
sure.
last part of his name, is it actually like 2 syllables? Singha? Is that?
Yeah.
Singha.
Yeah, we asked him.
Singha, yeah.
Yeah, I asked him before we started to make sure. I was like, I want to make sure I'm saying. And he said Wickramasinghe is how he pronounced it. Yeah.
Wickramasinghe. Okay.
Yeah.
Okay.
Yeah.
So
a couple other interesting points that he talked about. There's evidence of smallpox lesions on Egyptian mummies. I find this fascinating. Right. So I think this was in his Disease from Space book.
Mm-hmm.
Evidence of smallpox lesions on Egyptian mummies. So we're talking very old. And then all through the classical period of Greece and everything, there's no evidence of smallpox, even though there's lots of records about diseases that were coming, the Athenian plague, everything like that, but no smallpox. And then it suddenly reappears, and he thinks that shows that this may be a long cycle of something coming in.
Yeah. Now I would also like to point out that some of the critics to this idea are saying, well, how come if let's say this COVID-19, and if it came from space, why is it so similar to these 18 other strains or whatever of the coronavirus that are in these animals that are terrestrial? And the point is that if we live in this, like what Randall says often, this cosmic environment, and there is how did you put it? The
cosmic microbiome.
Yeah, cosmic microbiome. And it's been raining down on us for billions of years. So it would make sense that things coming from space today match things, look very similar to things that are here, because we make our way around the galaxy. This was another thing he pointed out. What is it? 250 million years. We go all the way around the galaxy. And if all the exoplanets in the galaxy are being occasionally bombarded by cometary objects, which also might be carrying biological precursors or whatever, but these planets that might have life on them, it's throwing all of that stuff into orbit and possibly escape velocity from their star systems. And so it's floating around in space. We eventually travel through it. So it's like the whole galaxy of exoplanets has been sharing this biological material for billions of years. And that's just freaking
yeah,
I'm just like,
that
oh
was
my
really
God.
cool. Yeah. So Earth has been doing this too. Every time the Earth has been impacted, some material gets ejected all the way out into space, and some of it gets escape velocity from the sun, and that means that the biological material that was here at that time, at least the microbiological stuff, some of it, will survive and eventually seed other exoplanets in the galaxy. That
and you know,
is really cool.
Planetary geologists have actually found fragments of Mars on Earth.
Right. Yeah, fragments of Mars here. Yeah.
So you've had the big impacts on Mars. It throws debris into space. Earth will sweep up some of that stuff.
Right.
Likewise, debris from the moon.
Yeah.
Right.
There's also been a recent story we talked about or reported on it on our podcast a while back, but they have now discovered like a protein molecule in an asteroid that they recovered. You know, say asteroid. I'm sorry, a meteorite. That they discovered, and they've written the paper. I don't think it's been peer reviewed yet, but yeah, they think they've found protein molecules. So we need space protein shakes. Basically, we got to have those.
Also, stock the crystal spaceship with protein.
Yeah, there we go. The other thing we talked about that was interesting, and this was recent as well, is the stuff that keeps building up on the windows of the International Space Station, and the Russians the cosmonauts are going outside to clean off the windows because the windows are slowly getting fogged up with material. So they go out there and they clean it off, and then they bring the whatever the rag is that they use, they bring it back inside and they test it, and it's biological material, plankton in some cases, right? So we call it space plankton. We talked about the space plankton. He said, that's 4,000 kilometers above the surface of the Earth. It is. You can't explain how that stuff got up there.
You could say that it was from extremely ancient impacts that threw that stuff up there and has been orbiting around the Earth ever since, right?
Right. Yeah.
But if it's still viable,
it's still alive.
That means that it's happening on the rest of the exoplanets in the galaxy as well, and we're running into that dust as we travel around the galaxy. So it's like, I don't know. I'm buying it.
Yeah. Yep.
And there's so many articles there on the cosmic dust that you can get some background on Dr. Chandra Wickramasinghe and the things that you guys talked about in the podcast. It's just full of information there. And one of the things, in addition to what you already mentioned, is so fascinating is it seems to be linked maybe to a lack of sunspots,
Yes.
And it reduces the magnetic field of the planet, and that allows more of these to drop in to the atmosphere. So he had predicted months ago that one of these periods was going to be upcoming, and we need to be watching out for some new virus, as happened 100 years ago. And he said that months ahead of time.
Right.
And what it is when there are no sunspots, you've got a less active sun.
But wait. Other scientists have been warning about, pandemics too. They don't necessarily have to come from space.
Well, listen to the reasoning though, Mike. Go ahead, Randall.
That's right.
Oh, well, I was just going to throw in the detail that the solar wind acts as a buffer that will sweep away cosmic, microbiotic cosmic or any microscopic material
right.
Yeah. So when the sun is less active, it's just like if you've got a wind and it's blowing the dust away, right? And then you've got the wind, loses velocity or whatever. And so now the dust begins to settle. So when you have a lesser active sun, right, you have now more cosmic bombardment, more cosmic rays can penetrate the atmosphere and reach the Earth. So that's the idea there.
That's right. Yeah.
And you're right, Mike. I mean, yeah, people have been predicting the end of the world forever. So
not predicting the end of the world, but there've been warnings about pandemics for several years now. So,
yeah.
We should be expecting one.
Yeah, it's inevitable, right? I mean, that's the idea.
Well,
it's
and to elaborate on that idea a bit, one of the things that I'm looking at quite a bit and which we're going to be covering is this idea that incursions of cosmic dust, whatever the source, and it usually could be comets that are, ultimately, at the final evolutionary stage of a comet without actually being sucked into the sun or a planet is basically cosmic dust. And even there, its ultimate it's the ultimate consequence is that it's going to usually be sucked up by some gravitational source, whether a planet or a sun, right? Well, so if you have this increase in cosmic dust, you also have an increase into the atmosphere, then you have an increase in the opacity of the Earth's atmosphere, which reduces the amount of sunlight, which now there's a pretty solid body of evidence suggesting that the amount of cosmic dust in the atmosphere can have a pretty major effect on the global climate. So if you get this accretion of cosmic dust into the atmosphere, increases the opacity of the atmosphere, increases the reflection of solar heat back into space, you now have a cooling of the climate. This could very well have been a part of the explanation for the Little Ice Age, because you had the Maunder minimum, you had the Sporé minimum, the Dalton minimum, and these were correlated with the coldest sections of the Little Ice Age, correlate with some of the lowest activity periods of the sun. So you've got this cosmic connection, and then you have a terrestrial connection in the form of volcanism, because, for example, during the Maunder minimum, it seemed like you had low solar activity. So now you have the potential of the solar wind blowing away less cosmic material, which can enhance the accretion of that. And now you've got add into the mix volcanic activity. Now, one question that I find interesting, is there a correlation between solar activity and terrestrial activity? And I think that we're seeing some tantalizing evidence that there possibly is. But
wasn't there like a pandemic or a plague or something during the Little Ice Age?
Yes.
During the Maunder minimum. So yeah, I thought that one of the other things that I found extremely fascinating about it was the idea that these impacts that cause the mass extinctions are also bringing with them all this new life, the potential for new life with these and so we see that in the fossil records, like everything gets destroyed, and then the next thing you know, you've got all these new species.
Right. We'll come back. Keep that idea in mind, because I want to come back to that in a couple of minutes. Let me finish this thought, which is that, of course, when you have this cooling of the Earth's climate, like we see during the Little Ice Age, or we see at the onset of the Dark Ages between 536 and 540 AD, which is another really important time that we should talk about, we have evidence that you had this conjunction of both volcanic activity and cosmic activity. 536 AD is considered one of the coldest years of the last 2 millennium, right? Now, you get this global cooling. What happens? Well, you then have agricultural collapses. You have food crops dying in the fields. You generally get cold. You'll get damp because of the lack of heat. It leaves the crops damp. They die in the fields. Now, people are going hungry. They get hungry. After 2 or 3 years, they get weak, right? Now, once they get weak from malnutrition, now they become more susceptible to a pandemic. And what we see in the wake of the 536 to 540 global cooling, what did we see? We saw the Justinian plague, right? Wiped out huge numbers of people in Europe, where we have a historical record, probably in other places around the world too. Come forward to about 1314, we have the fairly rapid end of the medieval warm period and the onset of the first phase of the Little Ice Age. And again, what do we have? We have agricultural disasters on a vast scale. We have people going hungry. They get weak. Their immune systems are compromised. Now they become susceptible to these pandemics. And that's when you had the bubonic plague, right? That wiped out a third of the population of Europe. Now, if the cooling is being brought on by an incursion of cosmic dust, is that cosmic dust also bringing in the material, the microbiotic material that could be triggering the infestations? In other words, the material's coming in normally, right? And we'll for the sake of argument, let's say that humans are going to be mostly immune to this, mostly, but not always, with clear exceptions, right? But in a case where you have not only the global cooling and the malnutrition. And then you have the incursion of these of this microbial material. And now you've got large segments of the people whose immune systems are compromised. Maybe it's these combined elements that really trigger some of these really horrible pandemics in history. That's where I'm trying to go with this.
Yeah, that makes sense. That there's a convergence of all those different variables that makes it really bad.
Yeah. Yes.
Yeah, and there are a lot of crops that grow in colder climates. So if you're farming and your climate changes and gets colder, you can grow different crops that grow in cold, damp environments. But if the crops are also being infected by things that they're susceptible to in this process, then you can have massive crop failure across the board and famine and all of the above.
Right, or it does something, complicated, like kills off a certain kind of bird, and that bird usually eats this kind of bug, and that bug then eats all your crops. I mean, there's all kinds of ways where it can collapse. So
yeah. The ecosystem interactions are amazingly complex, incomprehensibly complex.
Yeah. And Mike, I was going to say, Mike, you're right that, people have been predicting it, but it doesn't, where the source of the virus is in question still. But, I mean, did it, so did this current one come from wet market? Did it come from a biolab, or did it come from space? Nobody really knows. The current people, the accepted idea is a wet market. What do they call it when it goes through multiple species? It has to go from a bat to a snake to a person or whatever, because it can't go directly from a bat to a person. So it has to have some intermediary.
Right. I mean, you've got that. They're theorizing that happened with this virus in Wuhan.
Right.
But we saw the same thing happen with Ebola in West Africa, from bushmeat to humans.
Yeah, that's what I'm saying, is that they're always going back. We talked about this a little bit with Dr. Chandra, that they're going back to look for patient zero, and they're expecting patient zero to have some kind of unique interaction with something that gives them the virus that then spreads to everybody else. But it's almost impossible to find, and most of the time it's just left as this is the hypothesis, but nobody really knows.
Well, I think, and here's the thing: wherever it starts, whether it's in humans or in animals, it had to start somewhere. Something triggered it.
Yes.
So what we're talking about here, I don't think precludes the idea that certain species could be susceptible to certain types of viruses, microbial viruses. So if a bat is infected, it had to have come from somewhere.
That's right. Yeah.
Right. That's the unresolved question that I think Chandra is addressing. And I need to refresh myself on the details of his work. And I'm sure there's a lot more to it since 1979 or ever, when I read their book originally.
Yeah. On the subject of...
Didn't he say that, Russ, specifically about the Ebola? And you kind of touched on this earlier, that the emission spectrum or something of these dust clouds in space, they get the identical
E. coli.
Yeah, it was not Ebola, but yeah, okay, E. coli bacteria is the same thing that they're seeing, that these clouds out there are organisms or groups of organic material.
Yeah, they have pretty much the same absorption, pattern spectra as E. coli, which, doesn't necessarily mean it's E. coli, but it's really interesting. Yeah.
There's a frightening thought.
Right.
Yeah.
Clouds of E. coli in space.
We are in the bowels of the universe.
huge galactic-sized clouds of it. Yeah.
Yeah, in the bowels of the galaxy. That's right. He also said that early tests of the current, the novel coronavirus that's happening right now, early tests of people from China, and then people when it showed up in the United States, there was a guy that Chandra trusts as a geneticist or whatever, who was looking at this. He was sequencing it, and he said that there's almost zero variation between these two very disparate parts, where he's like, okay, so if a person from China, and you expect if it's person-to-person transmission that it had to go through who knows how many people to get to somebody from in the United States, it had to go through at least 3, and each time it does that, it replicates in a person and then it affects somebody else. There's not a mutation, but there's a change in the virus. It changes because it's being replicated in somebody's cells, and then that goes into somebody else, and then it replicates in their cells, and that infects somebody else. And each time that happens, there's changes. But the guy said there was almost zero variation on these opposite sides of the world, which Chandra was talking about. He said that implies a monoculture infection source. In other words, it's coming from the sky, and all those viruses are the same. So very interesting stuff there.
And that would imply that there's like a cloud of this stuff, clouds of these viruses floating around, like you're talking about the E. coli. That's hard to get your head around.
Yeah.
It's revolutionary, really. And as George Howard put it on his Cosmic Touch website, the podcast that you guys did is the most important podcast ever. So, get over there and listen. I was
thanks, George.
Freaking pegged, man. It is fascinating, extremely fascinating. I'm going to listen again.
As a comic aside, have you guys been watching this HBO series Avenue 5?
I haven't.
No, sir.
Check it out. It's really it's a sci-fi comedy. It's about a luxury space liner going out on a mission out into the solar system, a tourist mission, basically taking several thousand people out on a tourist mission, multi-years, back to Earth. At some point, of course, something goes wrong. They lose gravity. They shift their course, and they're going to be stuck out there for far more years. One of the subplots in this is one of the insulating factors for the ship is the ship's waste. Okay, the sewer, basically the sewage. They use the sewage to insulate the ship on the inside, right? The walls of the inside. And at some point, it springs a leak. So this cloud of human feces and waste material begins orbiting the ship. So it's circling around this. It's guided. You see images of this spaceship gliding through space with this ring of brown around it. It is hysterical. You just check it out. Avenue 5 on HBO.
Awesome. Thanks, Mike.
Thanks for that detail, Mike.
Hey, comic aside, that's what I'm here for.
Should we take a break and then get into plutonium and some other stuff, or I don't know. Just
platinum, Brad. Platinum.
No, plutonium. It's much more fun to say. Plutonium.
So, we could do a break, but
I'm not sure where we are timing wise. I'm just thinking maybe we're a little more.
I just got one more thing to say about
platinum. Sorry.
Chandra's work, Dr. Chandra's work.
Please do.
I think I've just been thinking about, once again, the Carolina Bays and how there's this, the Venus flytrap, which doesn't exist anywhere else in the world, is inside these bays.
Mm-hmm.
How might that have come about?
Yeah.
Well, that's a good point to segue into some discussion about the platinum group metals.
All right.
Good deal. All right, welcome back, ladies and gentlemen. We are now going to segue into the platinum group metals and primarily their delivery to Earth. Right?
Mm-hmm. Yeah. Platinum group metals are a signature for an extraterrestrial event, a proxy, if you will. And this brings us back to the Younger Dryas events and the discovery of a platinum spike. So I'm not sure how to pronounce his name, Mikhail I. Petiev. He wrote an article that it was in the Proceedings of the National Academy of Sciences back in 2013. And he was looking at the ice cores, Greenland ice cores, at the stratigraphic level of the Younger Dryas boundary, the Balling-Allerod Younger Dryas boundary at roughly 12,900 years ago. And he found something. So then he says in his article that appeared in PNAS back on August 6th of 1913, the impact hypothesis, once declared dead, and we've talked about some of the work that he's referring to there that did declare the impact hypothesis dead. In fact, there was even one article that was entitled something along the lines of, cosmic impact hypothesis, a requiem.
No, sorry, it wasn't 1913. It was 2013, right?
Did I say 1913?
I'm pretty sure you did.
I think I did, yes. I apparently was going back to somewhere in the back of my mind was thinking about the Great Meteor Procession of 1913.
Yep, sorry.
But that's not this episode. That's a hell of a story, by the way, and we're going to get into that.
Let's do that.
The Great Meteor Procession of 1913. Anyways, yeah, 2013. Hey, look, sometimes I get off a little bit. What's a century here? What's a century there? I mean, come on, Brad, cut me some slack, man. Okay, so he says the impact hypothesis, once declared dead, recently gained new support from the discovery of siliceous scoria-like objects. We won't get into talking about what those are right now, but we will, because that is one of the important proxies. That and the character of these things is this very consistent with them being born out of a cosmic impact type event. So these SLOs, or siliceous scoria-like objects, have global distribution, and they provide strong evidence for processing at high temperatures and pressures consistent with a cosmic impact. But the discovery of the SLOs alongside, and this is the key, abundant compositionally similar microspherules in 3 Younger Dryas boundary sites in North America and Asia is difficult to explain by anything other than a cosmic impact. We have tested the Younger Dryas boundary impact hypothesis by measuring trace and major element concentrations in ice samples from the GISS-2 ice core across the Balling-Allarod boundary. And then just a few highlights from his article, their article, actually. It was multiple. I think it was 1, 2, 3, 4 authors besides Patave. So what he discovered, that there was a platinum anomaly right at the boundary. And he also discovered that it was accompanied by a extremely high platinum iridium and platinum aluminum ratios, as he says it, indicative of a highly unusual source of platinum in the ice. Materials with a high platinum iridium ratio and essentially no aluminum, which is what he found basically, are known among magmatic iron meteorites. Until the question about the nature of the platinum-rich material and the means of its delivery to the ice is resolved, an extraterrestrial source of platinum appears likely. Because one of the things about the platinum group metals is their rarity in the crust of the Earth and their abundance within meteorites and possibly comets as well. For example, the platinum anomaly could be explained by multiple impacts of an iron meteorite. The main conclusion of our study is the detection of an unusual event during the Balling-Allarod Younger Dryas transition period that resulted in deposition of a large amount of platinum to the Greenland ice. One of the plausible sources of the platinum spike is a metal impactor, which is interesting because that's really a very different conclusion than what some of the other evidence is leading to. One of the plausible sources of the platinum spike is a metal impactor with an unusual composition derived from a highly fractionated portion of a protoplanetary core. Now that to me is really interesting. Yeah. Yeah.
Yeah, I was going to say, it's weird that there's very little of these metals in the Earth's crust, but there's so much of it in these objects in space, which implies, like, what does that imply? Why should that be?
For one thing, you got to understand that these platinum group metals, like iridium is a perfect example, is a siderophile. It loves iron, so it bonds to iron, right?
Yeah, okay.
So in the formation of the of the Earth, presumably when the Earth was going through a molten or semi-molten phase, the high density iron is going to sink towards the core. Well, it's going to drag all of the PT with it.
See? All right.
So if we could dig down to the core of the Earth, we'd probably find a lot of platinum. That's why he's saying that this much platinum seems to suggest a protoplanetary core.
Yeah.
Like, was there a planet that once existed that then, somehow disintegrated or exploded or right?
Yeah.
So now you've got these iron-like meteorites loaded with platinum, and now we're finding that platinum in abundant in that layer, that Younger Dryas boundary layer in the Greenland ice sheet.
So I have a question. Are any of these metals are, because I know that when these things come into the atmosphere, they heat up and they cause all kinds of different, maybe similar to smelting happens when they're falling. Is that happening, or do these metals exist as we find them in a meteorite? They exist the same out there in space before they come into the atmosphere?
No, I'm going to think that they probably have undergone some degree of metamorphosis. It's a good question. I don't know the exact answer to it. It would seem a reasonable assumption, though, that obviously in the tremendous heat and pressure of a meteorite impact onto Earth, that you could have some type of a metamorphic effect. I am going to do a quick share screen here so people can see this chart that was included in the Petave paper. So here we have several things going on. We see iridium in parts per trillion. We see platinum here. A is iridium, B is platinum, and C is volcanic SO4, which some of the critics said, well, this stuff you're finding is volcanic. So what he's showing here is the dates along the x-axis on the bottom. So what you'll see here is this transition, what he's calling the transition period. And right here, you see this huge spike of platinum that occurs. And if you follow this down, you'll see that this is getting right there between 12.8 and 12.900. That coincides precisely with the Younger Dryas boundary. And then if we go to this one, we'll see that the ratios in the JISP2 ice samples across the Ballingall rod boundary vary between chondritic and continental crust values. The only exception is the PT anomaly. So in other words, they're looking at the dust, and the chondritic could be part of the steady rain of dust that's falling on the Earth. Then the other type of dust would be continental. Wind is going to pick stuff up and blow it, and it's going to deposit on the ice, right? So they're finding that, but then they're finding this exception, which is the platinum anomaly, with both platinum/iridium and platinum aluminum ratios greatly exceeding chondritic and crustal values, with 3 top points also exceeding the platinum iridium ratios of low iridium iron meteorites. So here we go. Here's your question right here. Such a large fractionation of both platinum iridium and platinum aluminum ratios within the anomaly most likely results from atmospheric processing of the platinum rich material. And so again, here you see the spikes right here. So here you've got the platinum aluminum, platinum iridium spikes right here. And here's showing the various, so down at this level, you have the chondritic dust. At this level, you have the continental dust. But then when you get up into this level, now you're looking at low iridium irons. Okay, so this is rather contradictory in a way to some of the other findings, which we will be obviously discussing in detail. He says, our results could be explained by the impact of an iron meteorite with low iridium and high platinum concentrations. And then he gives the example of the Sicotte Alin meteorite fall and the Grant, which were two meteorite faults where they were actually able to study the composition of the material and discovered that they had ratios similar to the ratios that they found in the Greenland ice. So the former, which is the Sikhote-Alin, is a large crater-forming meteorite shower. If the platinum peak is caused by an iron meteorite impact, then the observed gradual ingrowth of the platinum concentration in ice over approximately 25 years requires lifting the impactor's material above the stratosphere and the formation of a ring around the Earth. The decay of the platinum signal is consistent with approximately a 5-year lifetime of the dust in the stratosphere. Such an impact could result in a global platinum anomaly. An anomalous 50 centimeter thick ice layer with 100 parts per trillion of platinum would require a sub-kilometer sized iron meteorite to account for the platinum mass balance. Now, that's assuming that the platinum deposition is confined to Greenland. Obviously, a sub-kilometer sized iron meteorite is probably not going to cause a large-scale global deposition of platinum, right? The main conclusion of our study is the detection of an unusual event during the Ballard-Allerod Younger Dryas transition period that resulted in deposition of a large amount of platinum to the Greenland ice. The nature of the event remains uncertain. So that was 2013, right? And then if we come forward to 2017, we have another study that came out, which is a very interesting study and very important, because what this 2013 study, whose lead author was Chris Moore, who Brad and I had the privilege of meeting and actually going out in the field with to examine some Carolina bays back in, when was it, Brad?
2017.
2017.
Late 17, yeah. Mike was there for part of that too.
Yeah, Mike was there. That's right. You were there too, Mike. So 2017, the same year that this paper came out that I'm going to refer to here now. So get up to it here. A lot of interesting stuff about the Younger Dryas did get published in 2017. So this title of this paper is Widespread Platinum Anomaly Documented at the Younger Dryas Onset in North American Sedimentary Sequences. So here was the question. Okay, so we've got this platinum layer deposited in the Greenland ice. Well, is it anywhere else? Can we find this platinum layer? Now, the assumption was that it would be much harder to detect a platinum deposition layer somewhere within the terrestrial crust than obviously a Greenland, a layer of Greenland ice, right? So in this study, they wanted to look at, well, if we actually take core samples of the ground and we get to the Younger Dryas boundary, can we find that platinum spike? So in the paper, Widespread Platinum Anomaly Documented at the Younger Dryas Onset in North American Sedimentary Sequences. And previously, let's see, we had second author was Alan West, who we need to get on the show. Third author was Malcolm LeCompte, who, for those people that saw the debate on Joe Rogan from a while back, Malcolm LeCompte was the investigator and geologist that we brought on to discuss his work in the debate with Michael Shermer. And then a number of others. Albert Goodyear was a co-author of this paper. Al Goodyear is the lead archaeologist at the Topper site, Younger Dryas Boundary site, which Brad and I, you were on that too, weren't you, Mike? The visit to the Topper site?
Or yeah, that was yes, the Topper site.
Yeah, with Al Goodyear.
He didn't go to Wilmington, but he went to Toppler with us. Yeah,
you did go to Toppler. That's what I thought. Yep. Yeah, so that's one of the important sites, and that's one of the sites that they actually investigated looking for the platinum. And I guess that's why Al's name is listed. So, anyways, they begin by referring back to the paper I just quoted from. Previously, a large platinum anomaly was reported in the Greenland ice sheet at the Younger Dryas boundary, approximately 12,800 calibrated years before present. In order to evaluate its geographic extent, fire assay and inductively coupled plasma mass spectrometry, elemental analysis were performed on 11 widely separated archaeological bulk sedimentary sequences. We document the discovery of a distinct platinum anomaly spread widely across North America and dating to the Younger Dryas onset. The apparent synchronicity of this widespread YDB platinum anomaly is consistent with Greenland Ice Sheet Project 2 data that indicated atmospheric input of platinum-rich dust. We expect the platinum anomaly to serve as a widely distributed time marker horizon, or datum, for identification and correlation of the onset of the Younger Dryas climatic episode. This platinum datum will facilitate the dating and correlating of archaeological, paleontological, and paleoenvironmental data between sequences, especially those with limited age control. So here's 4 of their sites. We will go to the screen share here, and we will look at their graphs. Here we go. If we look over here, you'll see 4. We've got the Arlington Canyon, which we talked about because a couple of episodes ago when we were talking about the Santa Rosa Island and the evidence for firestorms and stuff there. This is one of the places they investigated. Murray Springs, which is in southern Arizona. Blackwater Draw, which Brad and I have visited, and the Sheridan Cave. These are 4 of the 11. And notice here, this is the depth in centimeters below surface, right? So this is the surface, ground surface up here. You come down, and between right at 500 centimeters depth is the Alarad Younger Dryas boundary. And you can see right there, there's this huge platinum spike. There's another interesting platinum spike right up here, which, what does that mean? Is it redeposition of platinum that was originally deposited here? Or does this signal a separate event, one that possibly wouldn't be as extreme as at the Younger Dryas boundary? But nonetheless, this is an interesting spike up here. We come to the Murray Springs and get the platinum. You'll see that within the Younger Dryas boundary, we have not only the platinum spike, but we find that there is this dot right here shows the depth at which a microspheral peak was found. And the little diamond or little square turned on its side shows that there was also found there a nanodiamond peak. If we go back here to the Arlington Canyon, you see that you've got microspherals and nanodiamonds deposited right here with that platinum. And then right at the end, at the top, at the surface of this Younger Dryas boundary sequence, there's another. How did that get there? I'm not sure, but there was additional nanodiamonds found up here. Go down here to Blackwater Draw, same thing. Here is your platinum spike, this blue spike sticking out here, showing this very large increase in parts per billion, and also associated with microspherals and nanodiamonds. And of course, this represents the Clovis culture, and that the Clovis culture was existing up to the Younger Dryas boundary. So no Clovis culture in the aftermath. Finally, we got the Sheridan Cave platinum. And again, same thing. We've got a platinum spike associated with the demise of the Clovis culture and associated with microspherals and nanodiamonds. They also looked at Squires Ridge, which is, I think it's in, I don't remember where it is, but they looked at about 7 other sites in addition to these 4 that you see here, including the Topper site. I'd actually meant to get those graphs, but they basically will show the same thing. At every single site, there was a platinum spike, right? They use Bayesian analysis of dates from all Western and Midwestern study sites, which demonstrates a synchronous deposition of the Younger Dryas boundary layer within the limits of dating uncertainty. So there we go. They were wondering, well, is there going to be platinum detectable? Is there platinum detectable at the Younger Dryas boundary in continental sedimentary sequences? And so when they looked, sure enough, that's what they found. And in their conclusions, they state that regardless of origin, the consistent presence of anomalous platinum concentrations within sediments from multiple archaeological sites across North America that date to the onset of the Younger Dryas chronozone is compelling. Yes, indeed. The chronostratigraphic marker, this chronostratigraphic marker at the YDB, will be useful in geoarchaeological research for inferring the relative stratigraphic position of early Paleo-Indian, that is Clovis and post-Clovis occupations over large portions of North America, especially for sites lacking visual stratigraphy and or unambiguously stratified, well-dated archaeological assemblages. In other words, you now have this platinum horizon that would have been deposited simultaneously across the entire continent. So here we have repeatedly Clovis cultural evidence below that, no Clovis culture above it. The same limitations discussed above for platinum also apply to methods of absolute dating of archaeological sites. Radiocarbon and optically stimulated luminescence dating rely on carbon and sand grains, respectively, that are subject to reworking and displacement. This study finds no evidence to contradict the conclusions of Patev. However, the previous one I was just quoting from, et al., that the Greenland platinum enrichment most likely resulted from an extraterrestrial source. Whether the platinum originated from the impactor or target rocks. In addition, our findings show no contradiction with the Younger Dryas impact hypothesis, although detailed evidence for such an impact or airburst is beyond the scope of this paper. Our evidence indicates that platinum anomaly is a useful time marker horizon, and the ability to locate this chronostratigraphic marker easily within deglaciated sediments is a significant finding. This time marker will allow more robust age depth models and facilitate understanding of the effects of YD climate change on early Paleo Indians, flora and fauna across the Baldwin-Alarod Younger Dryas transition. So what they did was they were at first doubtful that they would actually be able to find it, right? But they did. It's there all over. So that was a lot of platinum injected into the Earth's atmosphere. Now, what do we know about platinum? Well, we could go.
Maybe go into that next week, Randall.
Why are we at the end?
We are at the end.
The end.
Right. Yes. Right at the end here.
Okay. Well, we will pick that up then next week, and we will talk about some of the ideas in the ancient world about platinum. Which is
excellent,
because the Egyptians seem to be very interested in platinum.
That's intriguing.
Yeah.
How do you draw the sword from the asteroid or from the
from the stone?
That's right. Keep saying asteroid. I mean,
I will close with this one quote from the late Lawrence Gardner to show that sometimes we are willing to segue into a little bit more esoteric realm, a little more speculative than strictly hardcore academic. Okay. We do that here. We are willing to go out on a limb. Okay. So Lawrence Gardner, in his book, Lost Secrets of the Sacred Ark, ARK, right? It is now plain from discoveries relating to the distant BC years that the ancients were fully aware of the individual properties of these platinum group metals. Yeah, that's a That's worth a few.
It is.
Stay tuned.
Stay tuned, folks. Next week.
It's been fun, guys. As always, it's always great to see your faces. And hopefully in a not too distant future, we'll all be able to get together and have a great big group hug.
Yeah.
Touching a lot.
Well, maybe not you, Mike, but
right now. I was going to say, Mike, I am not hugging you.
I appreciate that.
I'll hug Mike.
Brad, you got any updates on what's happening with the video channels? You want to talk about?
Yeah, I'm trying to keep up with it. You know, there's a few people that seem like they're confused, but we just want to get everything on the new Randall Carlson channel. So there's some old episodes coming in between the new episodes, but I've set up some new playlists, and people just have to pay more attention of what numbers.
Right.
You know, I'm doing the best I can here to get it all on this single channel, and we're transferring away a few things from Geocosmic Rex. There were still got a few videos coming up there. The Cosmographic 101 series.
Oh yeah,
was very complimentary and pertinent to what we're talking about in these episodes right now. And Comet Holmes about what it takes to bring in the comets from the Kuiper disk and the Bucket Brigade from the outer alignment of the planets. I mean, it's so pertinent. I love it. And that's gonna break tomorrow. So yeah, just trying to keep up with both channels, and eventually, you know, the people that come in new, like if there's a Joe Rogan podcast and Randall introduces a bunch of new, it'll all be the same to them. But you know, thank goodness for all the people that are with us now, but there's a little bit of confusion because they don't remember which ones they've seen and not seen because there's some overlap here. But you know,
right.
Well, then you just
ignore us for 3 months and come back, and it'll all make sense. You know, but some people want to be right on it right now, and they're not keeping up. So sorry about that. But
in the meantime, go back to episode 1 and rewatch every single one.
Yeah,
there you go.
In order.
Exactly. Start with
clearly
1.
That's what needs to happen. Yeah,
and hopefully at the end of that, you'll be smarter than you are right at the moment.
And it's totally fine if you watch 1, 2, or 3 times, because there's so much information coming so fast that as your brain goes on this tangent, you miss 3 things. So, you know, listen again.
Yep. 33% brain expansion guaranteed.
Guaranteed.
I guarantee it.
Well, that's why I'm always hammering on this idea of repetition, reiteration. You know,
right.
That's the core to really getting it in your brain. Otherwise it's superficial. You know, you want to learn how to do, you know, when you're learning math, you do the problems over and over and over again until you get it, you know, and the idea here is to really get these ideas in your brain. And that way you don't begin to see the patterns and the connections if what you heard 2 weeks ago is completely forgotten. You see?
Yes.
Well, and the people that tell me that, or say in the comments that, yeah, you can watch this in 2 times speed. I'm thinking, no, do not do that.
Right. But there are people that, there are some people that do that. We have people
then
that
you can watch it twice in the same amount of time.
Well, okay. Yeah, well, if they're watching it twice, I'm okay with it.
So anyone interested in the Scablands trip that we are hopefully still doing in September, right now it's still planned for September, check the show notes for the link. All the playlists and all the videos also will be down in the show notes for the links.
Yep.
The website's down there. The support. Thanks to everybody who's supporting us. I keep seeing the Patreon.
Absolutely.
More Patreon supports coming in.
Absolutely.
yeah, thank you guys so much. And links for that are also in the show notes. So
we're talking
about
doing a live stream.
Yep, that is in the works.
As a thank you, first of all, for Patreon supporters, but and then also one for everybody.
Yeah.
But if you're a Patreon supporter, we think we need to kind of give you something a little bit more esoteric, a little bit, maybe a little bit of a declassified material.
All right. What about the classified material?
So jump in. Patreons
well, we're declassifying it as we go.
Oh, okay. All right. That's right. So join the Patreon if you want to. If you can find it in the show notes, or you go to cosmographia.com. It's on the right. Patreon support and a link to a one-time donation through PayPal. So, and we thank everybody who has done that. You guys are helping us with the podcast and with future endeavors.
Absolutely.
All right. Anything else, guys? Great show as always. It was a fun conversation.
Yep.
Thanks, guys.
All right. Good night, gentlemen.
Genius.
Till next week.
5-star.
Good night, Brad.
Good
Mike.
night.
Randall. Thank you, guys.
Good night, guys.
Good night.
Oh, yeah, and good night, everyone.
You're going to be cautious and not say anything. Awesome episode!
How my cut? I want one of these times, like, what we want to do, we end the show and then Mike needs to start bitching everybody out. Randall, I told you.
Yeah, Mike can say, now you guys know you haven't been cleared to discuss that information.
Yeah, there you go.
This is Master Control.